The scramjet, or supersonic combustion ramjet, represents a transformative advancement in air-breathing propulsion. Its physics, design, and operational challenges are at the cutting edge of aerospace engineering, directly enabling sustained flight beyond Mach 5. India's hypersonic research ecosystem, led by organizations such as DRDO, Defense Research and Development Organization, ISRO, Indian Space Research Organization, and affiliated academic labs, is rapidly advancing the validated science and applied technology behind actively cooled scramjet engines. Fundamental physics, supersonic combustion, and airflow dynamics. Scramjet propulsion is grounded in the principle of compressing incoming air via aerodynamic forces, rather than mechanical compressors, with combustion occurring while the airflow remains supersonic. The engine consists of an inlet, isolator, combuster, and nozzle, all with contours optimized for hypersonic flow. Unlike ramjets, where the incoming air is slowed to subsonic speeds before combustion, scramjets maintain supersonic airflow throughout the combustion chamber. This design dramatically reduces drag losses and enables efficient high-speed flight. The key challenge lies in achieving stable, complete combustion within the extremely brief residence time available, typically fractions of a millisecond, before the air exits the chamber at speeds exceeding Mach 5. Active cooling, thermal management solutions. At these velocities, stagnation temperatures in the combustion chamber can easily exceed 2000 Kelvin, creating severe thermal stress on engine surfaces. Most conventional high-temperature materials, even advanced nickel-based superalloys and ceramics, will fail by melting, ablation, or cracking under continuous exposure. To counteract this, active cooling techniques are imperative. Indian scramjet research employs integrated cooling channels, often fabricated via advanced additive manufacturing or micromilling. Cryogenic or supercritical fuel, commonly hydrogen, or in some programs, hydrocarbons, is circulated through these channels, absorbing heat and simultaneously preheating before injection. This not only maintains thermal equilibrium, but enhances combustion efficiency via fuel preconditioning. Thermal sensors, embedded in the channel walls and surface probes, monitor real-time temperature profiles, enabling autonomous engine control to optimize heat removal and prevent thermal runaway. The interplay between cooling fluid characteristics, channel geometry, and wall material thermal conductivity forms a core research area in Indian hypersonics. Aerothermodynamics and combuster design. The combustor, the core of a scramjet, demands highly controlled mixing of fuel and supersonic air, rapid ignition, and sustained combustion. Indian testbeds use 3D computational fluid dynamics, CFD, validated by lab-scale wind tunnel experiments, to simulate shock wave interactions, fuel-air mixing layers, boundary layer development, and flame propagation. Shock trains, a series of oblique and normal shocks generated by flow discontinuities, can affect combustion stability. Indian experimental setups include optical access windows and advanced diagnostic methods, such as laser-induced fluorescence and particle image velocimetry, to directly visualize flame anchoring and shock train positioning inside the combustor. Effective fuel injector designs, often based on direct numerical simulation and rapid prototyping techniques, are evaluated for vortex generation, reduction of separation zones, and maximized mixing. These efforts converge on optimizing combustion efficiency, minimizing unburned fuel, and extending engine operational window across varying Mach numbers. 60-second subscale combustor test, technical achievement. A major breakthrough has been the successful 60-second hypersonic combustion test with a subscale actively cooled combustor. This experiment, conducted by India's defense labs, marks a leap in engine maturity, sustaining a stable heat release, avoiding thermal or mechanical failure, and achieving consistent flame propagation for the full run duration. The test environment mimicked flight conditions at Mach 6 using a high-enthalpy shock tunnel facility. Supersonic airflow, generated with appropriate stagnation pressure and temperature, passed through a custom-designed inlet and isolator into the combustor. Precision metering of cryogenic hydrogen as fuel ensured that target equivalence ratios could be attained at each sensor stage. Embedded data acquisition tracked over 1,000 separate combustion and thermal parameters in real time, wall temperatures, internal pressures, heat fluxes, and spectral emission signatures. The combustion process maintained uniform flame structure, avoided pressure spikes, or thermal choke, which could disrupt airflow and engine functioning. Exhaust analysis, using mass spectrometry and chemical probes, confirmed near-total fuel utilization and characteristic emission spectra consistent with supersonic combustion models. No material ablation, crack formation, or catastrophic wall loss was registered during teardown analysis. These results directly validated engine models developed using indigenous Indian CFD codes and high-speed computational platforms. Critical technologies, rapid maturation and system integration. India's hypersonic propulsion initiatives emphasize integrated system design rather than isolated subcomponent optimization. Beyond combuster and cooling maturity, progress spans vehicle aerodynamics, thermal protection systems, flight control integration, and multi-physics simulation. Thermal protection systems, TPS, required for vehicle surface survivability, are optimized using similar active cooling networks and advanced composite materials, ablators, carbon-carbon ceramics, and ultra-high temperature ceramics, developed in collaboration with national laboratories and industry partners. Electronic intelligence architectures, including high-speed telemetry, adaptive control algorithms, and fault detection via machine learning, are embedded into scramjet demonstrators. This enables autonomous engine modulation, health monitoring, and real-time thermal adjustment during flight. Combustion chemistry and diagnostics. Indian scramjet researchers devote significant attention to detailed chemical reaction pathways at extreme temperature and pressure regimes. Advanced diagnostics map key parameters such as local equivalence ratios, radical concentrations, and intermediate species formation. Diagnostics employ Raman spectroscopy, laser-induced breakdown spectroscopy (LIBS), and high-resolution infrared thermography. These approaches reveal transient phenomena like flame holding, local extinction, and shock-induced ignition, critical for refining engine design and combustion algorithms. The outcomes have direct consequences for fuel selection, injector geometry, combustor wall treatments, and active cooling strategies, bearing on scalability from laboratory to full system. Material science and structural engineering. Active cooling imposes stringent requirements on both engine wall materials and channel design. Indian programs explore a suite of refractory metals and composite ceramics, including niobium alloys, molybdenum silicides, and silicon carbide variants. These materials are subjected to cyclic thermal loading, additive manufacturing tolerances, and advanced joining techniques, bonding, diffusion welding, or friction stir welding, depending on channel geometry. Researchers conduct focused experiments to assess oxidation resistance, creep rates, fatigue limits, and fracture mechanics at high Mach operating conditions. Full-scale demonstrators are subjected to vibration testing, high-G load survivability, and rapid thermal cycling in ground and airborne platforms, ensuring the translation of subscale combustor success to operational modules. Flight test roadmap and validation. India has outlined a multi-phase roadmap for scramjet flight validation. Ground demonstrator, validated lab combustor and cooling modules integrated with simulated inlet and nozzle segments. Captive flight testing, scramjet engine mounted to air-launched and high-speed rocket boosters. Telemetry provides real flight data with optical windows and diagnostic ports for analysis. Free flight demonstrator, entire airframe configured for endo-atmospheric hypersonic cruise at sustained Mach 6+, coupling active cooling, precision guidance, and full TPS. Each phase involves escalation in operational complexity, environmental stability, control surface coupling, TPS thermal management interaction, and sustained flight time. Testing protocols employ recovered hardware analysis and post-flight component inspection, contributing data for next iterations. India's hypersonic propulsion efforts have converged multiple organizations. DRDO's Hypersonic Technology Demonstrator Vehicle, HSTDV, validated scramjet flight at Mach 6, achieving sustained combustion beyond 20 seconds in flight, with active wall cooling and integrated TPS. ISRO's efforts focus on hybrid propulsion systems and reusable launch vehicle platforms for space access at hypersonic speeds. Academic R&D. IITs, IISc Bangalore and CSIR labs contribute CFD modeling, combustion diagnostics, and material science breakthroughs. Indian technology is characterized by modularity, scalability, and indigenous intellectual property. Hardware development is closely married to model-based design, validated stepwise from numerical simulations to wind tunnel tests to live hardware. Cross-disciplinary teams integrate propulsion, aerodynamics, manufacturing, and flight control expertise, accelerating maturation cycles. The rapidly maturing technology base includes custom wind tunnels and shock tunnels for high-enthalpy simulation, additive manufacturing of complex cooling channel geometry and combustor structures, big data-driven diagnostics for engine health monitoring and autonomous control, direct scale-up pathways from subscale combustors to flight-weight operational modules, global context and strategic implications. India's scramjet progress parallels and increasingly competes with global leaders in hypersonic propulsion, principally the United States, Russia, and China. Unique aspects of the Indian program include emphasis on cost-effective, modular active cooling, deep integration of indigenous material science, and a robust national supply chain for key components at TRL, technology readiness levels. Strategic implications span tactical strike systems, rapid global reach, boost glide vehicles, and reusable space access platforms. Synergies with advances in TPS, thermal management, and autonomous vehicle control are positioning India as a technology innovator in the flight regime beyond Mach 5. As of late 2025, India has validated the critical science behind actively cooled scramjets, moving from short-duration combustor experiments to sustained test runs at record-breaking parameters. Data from the milestone 60-second subscale combustor test provides a robust foundation for upcoming flight demonstrators, integration with high-speed aerial platforms, and direct application to future hypersonic vehicles. The path forward involves integrated system flight at operational altitudes, full-duration hypersonic cruise, real-time adaptation to environmental conditions, and rapid cycle manufacturing of scalable scramjet hardware. India's active-cooled scramjet propulsion program embodies the convergence of advanced air-breathing science, applied materials engineering, thermofluid dynamics, and tightly coupled diagnostic feedback technologies. With demonstrated hypersonic combustion over full-length test durations, successful management of severe thermal environments, and rapid design-to-test cycles, Indian hypersonic technology is rapidly approaching operational maturity for next-generation national defense and aerospace applications.